called a little bit of a zoo of different things, a list of complaints. I have to go through them because I want to make my experimental friends happy. But now I'm trying to make it more exciting. I'm trying to push as hard as we can in several directions. Actually, there was one direction that I'm skipping because I prefer to go slowly through the things. And this part is about pushing on fidelity, how you can reach the best possible fidelity that the physical system gives you. I guess I won't have the time. Maybe if I manage to do it, I can come back to that later, but maybe not. And the two aspects I want to focus on are speed and size of quantum systems that I want to drive. And so here comes the first question. Okay, I have shown that we can speed up processes, but how fast can we go with such processes? And now there is a common feature between this place where I gave this talk, as I mentioned, Russia, and my own country where I come from, which is Italy, and Germany, where I live now. And it is very funny that there is something in common between these three countries, which is irrelevance of speed limits. In Russia, speed limits are relevant because no one knows whether there is any law on speed limits. In Italy, people normally know there is a law, but it doesn't matter. In Germany, it is forbidden by constitution to put speed limit on highways, right? And Mrs. Merkel said, I will not put it because it is not in the program of my government. So, unfortunately, quantum mechanics is different, meaning that we do have some limits here, in the sense that, okay, we can try to do our operation faster and faster and faster and faster, but at some point it will break down. And the reason is very trivial. We all know that it's some sort of time energy uncertainty principle. If I have some energy in a system, I am in a certain eigenstate. I want to drive this system to an orthogonal eigenstate. I have some energy scales, the initial energy expectation value of the Hamiltonian of my state, and also the energy spread. And the minimum time in which I can drive a system from one state to another state, orthogonal to it, is given by those inverse time scales, those inverse energy scales which give time scales. And this is something that Seth Lod and collaborators almost 10 years ago derived for a simple system, localized Q-level system. And what I am going to try is to extend this to bigger and better systems. We are in the US, so we are supposed to do things bigger and better, and this is what I'm going to do this month. So here is a first example. So the question here that I'm asking is, can I reach the speed limit with my optimal control? And if I do not know what is the speed limit, so if for a system I cannot calculate it very simply, as I showed in the previous transparency, as an inverse energy scale, can I detect such speed limit by doing optimization? Okay? And so here I have a very, very pedestrian heuristic approach. So the system I want to optimize is a Landau-Zener crossing. So it's a two-level system, and basically what I have there is just two levels which have an avoided crossing. There is a certain coupling here given by this omega scale. And what I want to do is I want to start in this state here and then go to the ground state after this crossing. And of course I could do it adiabatically as I showed in the first lecture, but I want to do it quick, okay, as quick as possible. And I should expect that I should be limited in this operation by this energy splitting here. So what I do is I pretend I do not know what is my energy scale here, and I just do optimization. Meaning, I prescribe a certain time for my Krotov algorithm in which I want to go from here to here. Okay? First very long time, and then shorten and shorten and shorten and shorten. And every time, I try to do my optimization in the sense that I iterate my algorithm, and as the number of iterations grows up to 10 to the 5, I see what happens to the error, to the infidelity in the final state. Okay? And so clearly I expect that if I do this for sufficiently long time, then the error I get can be very small and converge down to 0. If I take a short time, on the contrary, I will saturate this bound and I won't be able to push my system too much. Okay? And now I would like to know where the limit is. Okay? What is the quantum speed limit for this system? And intuitively, I have this series of curves, and this is very heuristic, as I said. Okay, it's nothing, no theorem, nothing mathematical, but I have an algorithm, I run it, and I say, okay, whenever this algorithm is converging, then it means I have allowed sufficient time. When the algorithm isn't converging to zero error, it means I'm trying to do it too short. It's impossible, okay? So how can I detect that? Well, intuitively, I can say if this curve has a negative curvature, then it means I am converging. If it doesn't, it means I am not converging. And so I can plot the curvature of these curves, which is extremely heuristic, as I said, okay? Because this is just, convergence curve of an algorithm. It has no physical significance in a sense. But nevertheless, if I can see when these curves cross zero, which is for this guy here, which becomes straight, so to say, I can check what is the value of the time there, and this value is 1.58. And for this system, I mean, in this case, this corresponds exactly to the up to 10 to the minus, fraction of 10 to the minus 2 in relative terms, to the speed limit to this frequency here that I have. Okay, this is I guess half pi, right? And so I'm trying to do I'm putting this coupling equal to 1 in this system, and basically this means if I am trying, I know nothing about the system, I'm trying to push it as fast as I can, and I check whether I succeed with this very heuristic method, then I can capture what would be the ultimate limit given by quantum mechanics for the evolution of this system. And of course, in this case, this is utterly useless because I knew it from the previous transparency, what it does. But in other cases of more complex systems, then it can be very useful because maybe I wouldn't know a priori how it would be. So, well, here is actually a check that what we capture heuristically, okay, what I promised, an error of the order of a few percent. So here is the estimate of the speed limit for different initial states and different initial conditions given by this method, and here is the analytical estimate given by the theory, and they go pretty much on top of each other. So we can start maybe trusting and using this in more complex situations. And here is the first instance of a many-body, a many-spin system where I want to apply this. Actually, this is a fake many-spin system because it is indeed a spin chain, but effectively it is a single quantum problem in the sense that I have one quantum here, one excitation, one initial state on one end of the chain, and I want to transport it, to use it as a quantum communication channel to the other end, and end up with the same superposition, alpha 0 plus beta 1, but at the opposite end. Why can this be? And this, of course, is like transport of one particle, which makes the analogy to the problems that I described before of transport, non-adiabaticity, and so on. Why is this relevant? Because I can use this, for instance, as a quantum wire between different processing regions, for instance, of a quantum processor. Here is a picture of an ion chip, which my colleague Ferdinand Schmidt-Kahler then in Ulm uses for quantum entanglement and quantum computing. So we can connect with such a channel and have one state appearing on one end of this channel, and then I can transport it through to the other end. This is an idea which Sugato Bose in 2003, almost 10 years ago, put forward, and again, it works very well, it is well understood adiabatically, but we want to do it non-adiabatically. So, how can we do that? So here is the Hamiltonian, how this transport works. I have couplings between those spins. This is a specific proposal that was from a few years ago, how to do that. And I can add a magnetic field, yeah, which is modulated in space, and I can move this through, and as I'm moving this, basically I'm modulating the coupling between the spins so that I rotate all of them until the final spin gets the state that was originally in the first spin. And here I have, as I had before, two control parameters, which are the amplitude of my field and the position of the minimum. And now I want to optimize that, because I can do this adiabatically, but I want to do it much faster. And so here comes a movie of my champagne, or maybe here I prefer Burgundy wine, traveling from one end to the other of the chain. If I do this adiabatically, so here is my magnetic field, I am moving it, here is a spin population per side. I want to transfer the spin, which was initially here, all to the other end. And so adiabatically, of course, I can do it very slowly. Pop, 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 and then what happens if I do the simple non-adiabatic thing? I just scale down the time, or in order to visualize it, I can make it with a shallower trap. So if I try to do it faster in a simple way, what happens is this. Here is a trail of broken burgundy glasses on the floor, and only part of it reached here, and this is really my non-adiabatic trail that I left behind. So now what I want to do is, of course, I want to optimize. Here is, as time evolves, you will see the amplitude of the field and its position modulated in time, okay, as iterations go on. So I start with a flat distribution, and then I run my algorithm, and what do I get? Of course, I get some wiggles, that's obvious, and in the end, I get some certain shape, okay, for my pulses, and I can now run my process with those different shapes. And this is how it works. I'm basically juggling, you see, I'm juggling the system, you know, I'm delocalizing it around many sites, and then I'm refocusing it, catching it again. And this is actually increasing the spread also in energy, and the spread is in the denominator of the quantum speed limit, which means that this will help me go faster, okay? Actually, how faster? More than 200, around 200 times faster than the adiabatic process, still with a very large fidelity. And so now for the next step of this experiment, I need three things. One thing is, of course, a computer, because I'm a theoretician. Second thing is a student, because I am a professor. And the third thing is a chain. This is not a spin chain, it is a chain that I use to connect student and desk. I will allow the student from time to time to go to the bathroom, to have a little bit of water, so that he can sustain himself like in the biosphere out there. In the end, what I want is, I want the student to run this for all possible values of length of the chain and for all possible values of time, and every time I want to make sure that the student has suffered enough that whatever he gives me is really the best that a human being can possibly obtain, okay? Because those algorithms, they do not always converge to the global minimum. You have to, you know, tweak and to play with them to make sure that, I mean, to be relatively confident that it works, that it does the best it can. And so I want to be sure for each length of the chain and for each time that this is the case, and then I get a nice view graph, which is this one. So here is a scale of the final fidelity after the optimization, okay? And there is a range from red, very bad situation to blue, very good situation, okay? And here is a graph as a function of the length of the chain and as a function of the time, okay? Here is the time. Actually, I divided the time by the length of the chain because somehow this is an extended system. I should expect that there should be some scaling as a function of the length. It should go linearly in some way. In fact, it does. And so I see asymptotically with increasing number of spins, I get a flat surface here. The interesting thing is, you know, here there is a whole range of colors between blue and red. And here it is deep blue, and almost suddenly, boom, you go into red. Meaning, if I'm trying to do it, you know, shorter, at some point I cannot push it any longer. I am reaching again a regime in which I'm not converging like before, and then I can say, well, maybe I'm capturing some speed limit here. There is some sharp transition here in a way, right? So theoretically, I would expect, I mean, if I use the elementary theory from Seth Lloyd, I would say, okay, I have to swap my spin from one to the other, my state from one spin to the next one, and so the maximum speed would be given by, you know, repeating such swaps. I can see that my control allows me to reach it, even in this slightly less simple system than before. It even allows me to do a little better in the following sense, that here is what I would expect in terms of the time it would need to do this swap as a function of the number of spins in the chain, if I used just, you know, swap after swap and used the inverse energy scales of the spread and of the coupling. J is the coupling between the spins from the previous Hamiltonian. So this would be what I would expect from the elementary theory. Now, if I do optimal control, of course it is still linear, So it doesn't change, you know, the complexity class, so to say. It's always linear, and it's only a factor of 2 or 3 in between these. But a factor of 2 or 3 can be important in experiments, can be certainly helpful. And moreover, when I am here in an experiment, I know I cannot possibly do any better. And this is also relevant information if I want to realize such processes. And in fact, I will show you examples from experiments at the end of the talk where people have been reaching that. So, but this was very trivial, like I have a spin and transport it, everything is well understood. Now we would like to do something slightly less trivial, slightly more complex. And here it comes. Now I want to do quantum computing, universal quantum computing, so this is just theoretical, this is not a proposal for some experiment, it is a concept, where I have many qubits, and I cannot control those qubits. The only thing I can control is I can do a Hadamard gate, a gate which takes a 0 state in a superposition of 0 plus 1, and a 1 state in a 0 minus 1, and the other thing I can control is the magnetic field talking to the first end of this string. So I have a very long string, and I can only wiggle one end of it. And what I want, and I cannot do anything in here. Okay? What I want is, I want to perform universal quantum computing between any 2 qubits there. How can I do that? I want to swap, to transport, to use this transport concept, to transport the state of 2 qubits here into the first 2, then do some quantum operation, and then back. What is the limit for this? Well, is it possible at all? This is something that you would not think possible, okay? If you tried to do this via some circuit model, okay, this would turn out to be, you know, inconceivable. On the other hand, you want to know how fast you can do this, because it would only be worthwhile if you can do it in a time that is sub-exponential in terms of the length of the chain, right? Otherwise, you lose your advantage with your quantum computer. So we did that with sort of general spin model for, you know, different values of this parameter gamma. You have a different possible spin Ising, transverse Heisenberg, and so on and so forth. All classes of different spins. You can change this only. Actually, we allow only to change the first magnetic field. What do we get? Well, here again we get a certain time dependence. Here, of course, it is much more complex than before. There are many wiggles in here. But on the other hand, if I look on the time scale of the natural energy, you know, coupling between the sides, this is not such a crazy curve. It is relatively smooth indeed. More importantly, how does the speed limit scale? So I have again my student, I do a view graph like before, and then I try to see what is the time that it takes to do such operations, and the time scales, this time quadratically with the length of the chain. Quadratically means still very much lower than exponential. Quadratic, why? Because I have 2 guys, and so that I want to make an operation with, I have to transport back and forth 2 excitations, so it gets more complex, and so it scales quadratically altogether. And then, as usual, I go to my experimental friend and I say, okay, can we think of doing this? And of course they start complaining, and in this case the complaint is one that I have not discussed yesterday, which is, well, I have mentioned it maybe, which is, well, you want a crazy pulse shape. I won't ever be able to do that because I need a very huge bandwidth to do that. My system is limited in bandwidth. I can only follow somehow my oscillations. Will this work? Okay, and then we thought, okay, maybe it won't work, so let's see. And again, we try to see this time a little bit more systematically than what I showed yesterday. What is the spectrum of my control pulse? And the first thing you learn is the spectrum has components only up to a few units of the natural frequency of your system, right? Of the coupling energy between the sides. But you say, okay, maybe it is very important to have those components because it is very delicate situation, so I have to do that very precisely. And then you say, okay, if I tell to some electronics, so to say, to control this magnetic field, I will give as input a very precisely shaped pulse, but the output will be distorted. It will be filtered out. It will be smoothened out. So what happens if what my system receives, if what my system feels is a pulse that does not have all these components. What happens, in other words, if I cut away part of the spectrum? Okay? How will the final fidelity vary with that? We can do this by cutting off spectral components from this spectrum and eroding more and more and more and more and seeing what the fidelity is. And the big surprise is if you cut down to the actually a bit lower than the typical energy scale for your system, so if you cut down to basically here, you still have unit fidelity. You can get rid of all this part of the spectrum, you can forget it, or you can do something else because your system experimentally does something else, and still you get unit fidelity. So it seems that these wiggles, I mean, this was actually a question that I think David Tyman asked me a few years ago in a workshop in Santa Barbara, and he said, okay, but maybe your wiggles are somehow primitives of control, right? Maybe you should think of your control in terms of, you know, what I can do using wiggles as building blocks. And this is precisely what we did. And of course we have a problem, because optimal control algorithms from NMR, for instance, have very fancy names, okay, very names of animals, of plants, of many nice things. There's the grape algorithm, a lot of very nice names. So we thought we have to come up with a nice name, okay, nice acronym. One unfortunate point is we forgot we were in Germany, so there is a little pronunciation issue here. And so our chopped random basis optimization algorithm is actually the CRAB optimization algorithm, and it is very important because in Germany this can be misunderstood as something else. That's nice. But let me explain how it works. So this is it. I have a small system, few spins. I want to have a big system, many spins. And I want to optimize it. And now, if I try to do it with a real many-body system, and I use this gradient method, I will fail miserably, because until now I used this Krotov method, but I was always in the one excitation, effectively with one particle machine. Simulation was efficient. If I am simulating a many spin system, then I need to use techniques like density matrix renormalization group and much more complex stuff. And this, just the simulation step, takes a lot of time. And so the many steps that I need, I showed you on the order of 10 to the 4, 10 to the 5, to have such algorithm converge, may be just unfeasible. So we need to simplify the problem. And I will show you the next slides how one can do that. Before I do this, I would like to come back to the cartoon I had in the first lecture, because I told you, that I would show you such a cartoon in a real setting where I have the energy levels for a certain system. In this case, it is a many-body system. It is a Lipkin model. Well, it is not many, because here I am talking about a few spins here, but the same thing holds if I have more. This is for the sake of clarity. I'm showing you few spins, and here the blue lines are the energy levels as I am varying some magnetic field, some external magnetic field. And the other colored lines are the lines that tell you what is the energy if I start in the ground state and I do some different types of ramp of time dependence of my magnetic field to go from one side to the other of this transition. So if I am going adiabatically very slowly, with a linear ramp maybe, I stay close to, with this yellow line, I stay close to the ground state, as I promised last time. If I do a quick linear ramp, then here, the minute I reach this critical gap region, then I start populating higher states and I shoot up with the energy. If I do the optimal control, I will give a kick in the beginning, and then there is some sort of complicated dynamics, and in the end, I converge down to the ground state. Okay? And again, I can now try and see what is the speed limit for this system, because this is no longer a simple system where I have one particle or maybe one excitation. It is a system in which I start really seeing some many-body dynamics. And so I try to see the speed limit. So what I show here is the error, the final infidelity in the final residual population outside of the ground state for different times here in which I am trying to do my process. And of course, if I have a long time, error will be basically 0. If I have very short time, I will have 100% error and just exciting things. And if I rescale actually the time as a function of the quantum speed limit time, I can do this. I can play this game for different many-body models. I can do it for these leaking red symbols. I can do it for some Grover adiabatic algorithm, entirely different problem. I'm trying to solve the Grover search quantum algorithm in a adiabatic way. Or I can try to do also a simpler system like this Landau-Zehnder optimization that I showed before. And here is the same curve I showed in the beginning, the analytic prediction for the simple system. And you see that they go all on top of each other if I scale as a function of the quantum speed limit. So there seems to be even some sort of universal scaling here that pertains to nature in a way, that a many-body system can be driven beyond what we know. What we know is from Kibble-Zurek theory, so to say. We know that if I drive such a system adiabatically for infinitely long time, I will do it with arbitrary accuracy. I will stay at the ground state. We know from, as I said, Kibble-Zurek, or if you like, in a Fermi-Golden rule sense, in a perturbative sense, if I go short, I will excite, and I can expect, in the limit of 0 time, I can have a sudden approximation, even in which I know that my error is of the order of 1. And I'm not really sure what happens around the quantum speed limit. Here, this scale is as a function of an action parameter that I define in terms of the total time that it takes for me to do the transformation and the energy gap there, because it is the energy gap that tells me how fast I can go. So, if I optimize, I get something universal in the sense that for values of this parameter bigger than pi, bigger than the quantum speed limit, I can obtain with optimization identically 0 error, which I do not have in the linear case. And there is also a universal behavior for smaller times given by this cosine square function. So there is something in there. There is something in many-body quantum systems that inherently tells you how fast you can possibly go. And these processes that realize this fastest transition can only be achieved by these optimal control methods. But again, we need an algorithm that allows us, a method that allows us to deal with a general many-body system. Like the spin models that can be simulated with these density matrix renormalization group techniques, so exact simulation in a reduced Hilbert case of many spin dynamics. Time consuming, it is not exponentially hard, it is doable on a real computer. You can do up to a few hundred spins on a classical computer, but still it takes time, and so you want a very efficient algorithm. And here comes our crab algorithm. So, as usual, you start with some initial guess. This is something, by the way, that I referred to it in talking to some colleagues and students. This is something that can be taught to your student, postdoc, whatever, within 1 or 2 weeks. We already did it for different, with different experimental groups. I showed the result in the end. So you ship us, your student, in a cardboard box. We feed knowledge into the student. Student comes back and can implement it in your system, whatever it is. Okay? And so this is really advertisement, if you would like, because it is simple, and in 2 slides I can explain that. I start with a certain pulse shape, and I want to modify it again to get a pulse shape that gives me better performance. How do I do that? I use my wiggles as primitives. So the function that is modifying the pulse is now no longer any function. It is written as a sum of a few basis functions, a few wiggle functions. Those could be sinusoidal, other polynomials, whatever suits best your system there. And now, what is the advantage of doing that? My pulse gets updated via this function here, but the complexity of this has been greatly reduced, because it turns out that, and this is again one of the things that come out from experience as this smoothness of landscape that Hirsch taught us since several years, and that we finally learned, the smoothness of the problem is such that a few such components, I say here 10, but typically 4 or 5 are sufficient, is enough to reach your goal. How do I reach my goal? I don't want to use a gradient because that is more complex computationally to compute. So I have, this is really a landscape in terms of, whenever I have this picture, I really, seriously, this is not a joke, whenever I see this picture, I think of Hirsch, right? Because this is really landscape where he is one of the biggest authorities. And a landscape means, it really looks like a landscape. It is some cost function, some goal function that you want to minimize or to maximize as a function of several parameters in your system. And now I have reduced complexity so that I have a few parameters. Here I'm depicting 2, but it could be 3 or 4. And where I'm starting from with my initial pulse is someplace high up. I want to go down. So what do? I calculate, this is a simplex method, I calculate the value of my cost function in a few points here, and then I let this little polytope, this little amoeba, roll down the hill in this way, and then I get something which is now no longer any crazy shape. This is a pulse which has a shape that I prescribed because I told which frequencies are allowed. So an experimentalist can tell me my pulse my waveform generator can do this and this frequency, and please generate me a pulse that does it, and we can do it. We just, this is really what we are doing at the moment. And so you don't need a gradient, you don't need any analytical solution, and you can optimize anything you wish. It should be something that you can either calculate, or even it can be something that you measure. So you can use this in a loop with your experiment, where the value of this function in any place in the landscape is not something you have calculated, but it is something you have measured. You try a certain pulse, you do the experiment, you measure the population in the excited state, you come back, okay? And this is working better than other feedback loop methods like genetic algorithms, because a genetic algorithm has no clue what your system is. It has no clue what are the frequencies in there. It cannot exploit knowledge you have on your system. Instead, this thing can. And to convince people that it works, in the beginning, of course, nobody believed that it could work, because it is, as I said, very pedestrian. So we took one example that is very widespread, very well known, and also very relevant in both from a condensed matter perspective and in terms of applications to quantum information and quantum simulation in particular, which is this Bose-Hubbard model, which is a model that tells you how particles how atoms in a lattice interact, and in particular the quantum phase transition that you have here is one that takes you from a superfluid, like a Bose-Einstein condensate, to a state in which, raising this lattice, you end up with 1 atom per lattice site. And here again, what is the ideal situation which I can achieve adiabatically? It is one where I have 1 atom per lattice site, which I can use as a quantum register for quantum simulation and so on. What is instead the thing that I get if I do it too fast? I get defects. Like, for instance, I could have one holon, so-called, so a hole here, which behaves like a quasi-particle, and a doublon here, so 2 particles here. And I don't want this, because if I try to do a quantum register with this, I will fail. So I want to erase those defects, and I want to make sure that I have a very clean multi-insulator state. Can I do that? Well, I can use my algorithm there in order to achieve this. I start with the usual linear ramp, which somehow goes down in a very trivial way. And now I try, the point is, I am trying to simulate the experiment that Immanuel Bloch and Ted Hensch did, and Tim Esslinger did several, and Marcus Greiner, by the way, did several years ago in Munich, with a comparable number of particles, but in a time which is almost 2 orders of magnitude shorter than that. So what I do is I run my Crab algorithm, I get some shape, which is, you know, not particularly, it is not telling you anything, you know, it is some shape that I get, and now I can see what this guy does to me. So here is the population, okay, without optimization. If I use a linear ramp, I have some defects, okay, population of sites is not equal to 1. If I optimize, it gets really equal to 1, and the energy per site can be brought down to 0. So, sorry, the particle number fluctuations can be brought down to 0, which is then correlated to the energy. So, how can I do that? Well, I now just need to employ the new pulse shape to achieve this. And if I compare this result over this time scale with any of the time dependencies that they normally use in such experiments, so the guess that you would use, either using linear or exponential or any other of the shapes that they have, would be that in the end you get of the order of 10% and up errors in your system over such a time scale here. But with our algorithm, you go down to, with optimal control, you go down to by 2 orders of magnitude. And both in the case of a homogeneous system, and if you put trapping potential, and so if you take into account aspects that they have really in this type of systems here. Now, they start complaining, so they say, well, I don't know really how many atoms I have in there, so there can be fluctuations, and so we can show that there is stability. So here is, if I have a number of particles in my lattice, which is not the number of particles that I used in my simulation, okay, I made a simulation with 20 particles, but I could have 22. And now if I have 22, instead of having, you know, 2 times 10, so 5 times 10 to the minus 3, I have 6 times 10 to the minus 3 in fidelity. So it is, you know, quite flat, and it still stays the error in the order of 10 to the minus 3. And so there is stability with respect to that. And I mean, we managed, based on this, to convince a few people to try new experiments. So here are some recent results that they obtained. And one is, the first one is very preliminary. This is an open loop experiment. We have not shown, I mean, this is not even yet fully analyzed the data. This is really almost raw data that I got from Immanuel, was it 3 weeks ago, okay? So here is our pulse. Linear pulse is this one. The optimized pulse is this different shape. And what they get is, with their normal procedure, which is already very much optimized in the sense that, I mean, it is state-of-the-art. This is basically the best one can do worldwide. They get some density of defects. So you would like to have this curve here equal to 1. And so they get it significantly lower than that, up to 20%. And if you use the optimization, this is, again, the first very preliminary result, but we see that we can suppress those defects. So we can do definitely better, distinguishably better than they did after several years of, you know, tweaking, tuning, and doing the better they can. So this is suppressing defects in the mode transition. With Openloop, like we deliver to them the pulse, this pulse here, and they did the experiment. It is a plug-and-pray approach. So here is another thing, instead in closed loop, because I said you can take this algorithm, this method, and instead of a computer simulating the dynamics, you can put the system. You try a pulse, you measure, and then you iterate. So here is an experiment with Massimo Guscio did with the same problem, so suppressing defects in a multi-insulator. And so they start here with some guess pulse. Here they have 2 parameters in the crab, and they, you know, move around, and you can see that they do converge after a certain time into this lower error region. Okay? And this again is something that I mean, we are writing it up actually. I just this morning I received a complaint from my assistant that I should read the paper so that we can submit it, but of course I couldn't because I'm talking to you about that. So here is another open loop example. Now it is not, well, one may think, okay, this is just a feature that works with maybe some discrete, some array systems, something like that. So we applied CRAB to an entirely different context. Here is a problem which Schmidtmeyer is working on. So he has this BC, Bose-Einstein condensate, on an atom chip. It is an anharmonic potential. And now what he wants to do, it is in the ground state, he wants to excite it to some first excited state in this anharmonic trap, because then he can get out of this state, he can get pairs of atoms with correlated momentum via decay from this mode. And again, I mean, they tried to do this, they could do it on the order of, in a time on the order of 10 milliseconds, but this was long for them because they wanted to do other operations in that. So we did our optimization, and we get again with CRAB a certain patch shape. And the features here are prescribed because they told us what their waveform generator can do. And we gain one order of magnitude in time, still with very high transfer efficiency. Actually, what our quantum speed limit theory would tell, because this is in principle a simple system in the sense that you know the gap here, quantum speed limit theory would tell you that it is half a millisecond. We are not quite there, probably because we have to take into account limitations that they have in their experimental system. So we are at about twice, more than twice as long as the quantum speed limit. But the nice thing is that they can measure it, and they have this first excited state, which survives for a certain time and then it decays, and it should be. And even what they claim, I'm not sure I believe it, because this is again preliminary analysis of data, what they claim is that the fidelity they get is even higher than the one in our simulation. So I guess that, well, I would have still 5 minutes, but we can leave them for questions, or I can tell you about the other.
So you started 10 minutes.
I have 10 minutes. Oh, fantastic. So I can even give you the other transparency that I erased. In any case, here I came, I wanted to make a consistent story, okay? And here is the take-home messages that I would like you to have. When you sit in your car, you need to park it, think of the dynamical algebra, your controllability theory will tell you whether something can happen. But then you want to know how fast it can happen, and for this you need maybe some quantum speed limit theory. And in the end, this would not be relevant if you would not be able to realize this. And for this, you need some wiggles, and there comes wiggling around your quantum optimal control theory that tells you how to make such things happen. And if you want to do it with many-body systems, then of course you have to use our CRAB algorithm, which is the only existing, to my knowledge, only existing quantum optimal control algorithm for many-body systems and quantum phase transitions. And that was the end of the story. So I thank you for your attention. Now we have two options. Either we have a little bit of